There we go.
This summer, my student was Aaron Conrad, who's somewhere over there. You can see him over there. He was working for me on something I'd never done before in my life. It's something that's far outside of my comfort zone, has nothing to do with my previous research projects. And as a consequence of that, it was really a process of discovery for both of the two of us. And so I feel like I am not qualified to give this talk in any way. I'm going to give this talk, and the only real reason why I'm up here and you're not up here is because I spent 4 weeks trying to read up on this stuff that you didn't spend, but that's the head start I've got and everybody else in this room. This is not something that reflects years and years worth of experience. What I'd like to talk to you about today is quantum computing. In particular, I want to talk about a specific way of accomplishing quantum information storage. But before I do that, I need to motivate what's going to happen, because at the end of this talk, I would actually like to invite Aaron Conrad to come up and show you an animation. And the animation is going to consist of a bunch of black dots. You might have even seen it a second ago as I was trying to sort things out. And the black dots will blink and shift around and disappear. And it'll be something that hopefully by the end of the talk you believe is interesting and exciting, as opposed to just being some animation of blinking black dots. So, with that teaser right there, let me go ahead and get started by giving you an outline of what I've got to do. And the majority of what I have to do is motivate the idea of why you should care about this stuff at all. What we're going to do is, first of all, explain why you would be interested in quantum computing. How does it work, and what advantages might it have to have a quantum computer over the computer you've got on your desk. And it really is a pretty specialized piece of equipment. It isn't just like what you have right now, but more powerful. Instead, it's designed to solve some very specific types of problems. And I want to appreciate what types of problems those are. And then we'll talk about what the big problem is with quantum computing right here. It's a problem called decoherence that arises intrinsically in the nature of quantum mechanical processes. And then we'll talk about a way that we might have to solve that central problem. And we'll go ahead and show the demonstration at the end, a little demo that we have prepped at the end of this. And by that point, hopefully everybody in the room will appreciate why it's an interesting demo. So let me begin here by talking, first of all, about the difference between qubits and classical bits. What's a bit, by the way? Some computer scientists. What can a bit be? It can be two things, right? It can be a 0 or a 1. Of course, those names are arbitrary. Those just represent two distinct states that element, that diode-like element of your circuit can be in. It can either be high or low, it can be on or it can be off, it can be a 1 or it can be a 0. And once you have the capability to store information like that, you can make anything else, right? Because if you can count in binary, you can go 1, 1, I don't know, 1, 2, 3, 4, 5, 6. Yeah, you can make any other numbers a combination of 1s and 0s. And then if you've got some way to modify the registers that store that information, you can actually do computational algorithms. You can add things together, you can subtract things, you can utilize different logic gates. All of that depends on the idea that this classical bit right here is in a well-defined state. It can either be a 0 or it can be a 1, but it's never both of those two things at exactly the same time. Quantum systems often come in that two-state configuration as well. Probably the simplest two-state configuration you encounter in quantum mechanics is the spin of a fermion. A fermion has spin. It can either spin up or it can be spin down. If you don't know what that means, don't worry about it too much. The important thing is it's a two-state system, and it can switch back and forth between those two states. But when you're dealing with a quantum mechanical system, you have an added layer of complication. And the added layer of complication is that quantum mechanical systems don't do one thing at a time. Instead, quantum mechanical systems can be some combination of both things happening at once. If there's a possibility of something happening, that thing that's possible to happen can happen at the same time as something else that's possible to happen. And so instead of having a register in your system that's either definitely a 0 or definitely a 1, you can be in this halfway in between configuration where you're both a 0 and a 1 at the same time. Now, if you scale it up to macroscopic levels, you get what we think of as the Schrödinger cat paradox, right? You stuff this cat in a box, you tie the cat's life cruelly to some external process like the decay of a particle, and until you open up the box and observe the cat is simultaneously alive and dead at the same time. Everybody's at least heard of that example, I hope. Something that kind of permeated out into popular culture to the point where you can appreciate what's going on. But you can see that this idea of being halfway in between two possible states is a complicated idea because it means your system isn't definitely anything until you observe it. By this I don't mean it's 0.5. This right here is not a state that's equal to 0.5, halfway between 0 and 1. This is a state that simultaneously is 0 and 1 at the same time. And when you go to observe this thing, it will decide what it wants to be. If it's in this state right here, you observe it and it's a 1. If it's in this state over here, you observe it and it's a 0. And if it's in this state right here, it flips a coin. If the coin comes up heads, it's a 1. If the coin comes up tails, it's a 0. And it can be in in-between states, at least for some systems as well. It might have a 75% chance of being a 1 and a 25% chance of being a 0, or some other combination like that. And until you perform the measurement process in quantum mechanics, these things don't have any well-defined value at all. You can make a combination of systems that are two-state systems like this, and when you make a combination of systems like this, quantum mechanics does something else even more remarkable. What it does is it begins to blur the lines that separate the unique identities of these objects right here. This right here is an optical lattice, and the optical lattice has locations where different atoms have been deposited. Each one of these things is a different atom, and these atoms have two levels. They could be either in a low state or a high state. And switching back and forth between those two levels is represented by these things being either red or blue right here. But when you put these things side by side, they have a way of communicating with each other. And what that means in quantum mechanical terms is that this thing right here begins to lose its own unique identity. Instead, it creates what we refer to in quantum mechanics as a wave function that incorporates both of those two particles, this one and this one, together into a single unified description of what's happening between both of them. And if you measure these two things, they can be correlated in some way. You can't just look at one of them by itself and expect the other one not to be affected by your measurement, because these things become entangled with one another. And that entanglement gives rise to a whole bunch of incredibly powerful quantum mechanical properties that we've only begun to explore in the last few years. For example, down here you can see a quantum entanglement can give rise to what we think of as teleportation. We can take a state that's over here and map the state that's over here perfectly onto an identical particle over here and replicate what's happening at this point in space over here at this point in space instantaneously. You don't need to shine it from one place to another at the speed of light. It just happens instantly, and it effectively has teleported that state from one position in space to another point in space. And the remarkable thing about that is it happens over incredibly large distances. That process right there effectively causes something at this position to be replicated at some other position right here. But the application I'm going to care about today from the standpoint of entanglement is what we think of as quantum computation. If you wanted to use an incredibly powerful computer today, what would probably be true about that computer? That computer would probably be what kind of a computer? Probably be a parallel computer, right? It would have lots of processors on board, and all those processors would be running at the same time. If you apply to a government laboratory for computer time, what they're going to do is give you time on a computer that has lots and lots and lots of different processors, and they want you to design your computer code in a way that can be distributed over lots of different processors all at the same time. And instead of running it on one processor for 17 weeks, they want you to run it on 17 processors for 1 week. And each one of those processors will independently be running a different thing that's happening all at once. Now the power of this system right here is that because quantum mechanical qubits, that is, the bits that are made of a quantum system like this, can be in a combination of different states at once, you can have a single set of registers and a single set of algorithms that effectively do the duty of all of those different parallel processors at the same time. You can have a single processor that is doing parallel computations intrinsically. You don't need 17 of them. You just need one of them with a single state that has 17 different possible configurations. And as you arrange these things in larger and larger lattices right there, you increase the universe of possible states all of these atoms can be in. They're all going to be entangled with each other, and there's a huge number of things that are happening all at the same time with a given probability. And that probability is something that isn't resolved until the end of the process when you can read out the final answer at the end. What kind of algorithms would a quantum computer be good at? Algorithms in which you want to run a whole bunch of different things all at the same time, and then you want to pick one of them out at the end. Anytime you can take a process and make it run in that particular way, make it do a bunch of things in parallel, and then grab one thing at the end, you have a good candidate for quantum computing. Let me go ahead and show you the sorts of things that we can do with quantum computing. Some of the things you can do are equivalent to things that you can do with classical computing. We have to design the logic gates in a slightly different way. This right here is a C-naught gate, and a C-naught gate in quantum computing is roughly equivalent to what you think of as an XOR gate in classical computing right here. But there are a lot of other gates that you can design using other quantum algorithms right here. And what you can see is that this C-naught gate right here is effectively a binary process. You've got 2 bits. One of the bits is a control bit. That's what the C is for, the C-naught. And if it's turned on, what it does is it takes the other bit and flips the other bit upside down. And if you take a bunch of these things right here, these C-naught gates, and you wire them together, you can make more complicated circuits. You can make things that perform in such a way that the algorithm functions as an adder or as a half adder, and all of those processes can be the processes that allow some algorithm to run in the same way that an ordinary processor works in a classical computer. There are lots of these other things right here, and the important thing to realize is if you can combine together enough logic gates, you can replicate everything a classical computer can do. And so a quantum computer, if you have enough of these gates implemented right here, will be able to do everything a classical computer can do, but it can do more things besides. Let's go ahead and think about the way this works. This is actually a very schematic diagram of exactly what you want to do with a quantum computer right here. And you can see it's got an extra step that occurs at the beginning of the calculation that you wouldn't see in a classical computer. A classical computer, you go and turn that thing on, and it's initialized into some state based on what's stored in its memory all the time. Quantum mechanical systems, you actually have to perform a measurement to initialize them. At least at the beginning, when you first turn on your register right there, when you first begin to interact with the register, it's full of random information. And that's always going to be true of a quantum computer. Every time you start with a quantum computer, it's always full of random information. And to make that quantum computer have memory that contains unique register values right here that correspond to 1s or 0s or linear combinations of 1s and 0s, you need to perform some initial process that corresponds to a measurement process to knock it all down into one particular state. Once you have that prepared, you can create whatever superposition you want, and then you can run these logic gates, let's stick a bunch of C-naught gates in the center right there, to represent combining together different registers right here. You've always got to have 2 registers for a C-naught gate. One's going to be the control bit, and one has to be the bit that's actually being operated on. And after you use a bunch of these things, at the end of the process, you have to perform a measurement. When you perform that measurement, it'll take all of the things that have been running in parallel on that superposition of quantum states and resolve it down to one particular state that you read off. That reading off process is to take the information in the quantum computer and pass it back to a classical computer, and then you'll be able to interact with the results of your parallel computation with all of this happening at the same time. What sorts of things can you do if you had a computer that worked in this particular way? Well, probably something that's relevant in the media at the moment is applications of Shor's algorithm right here. Shor's algorithm is basically a method for factoring incredibly big numbers. This thing right here is a prime number, and this thing right here is what's a prime number? A prime number is a thing that can't be factored any further. And if you take 2 absolutely enormous prime numbers, what type of number do you get up there at the top? You get a composite number, right? Because composites are made of primes, but how would you like to factor that thing up there at the top? That thing is a nightmare. That thing has an enormous amount of information built into it, and its only factors are gargantuan factors like the 2 things down here at the bottom. As it turns out, current encryption technology, the technology that's utilized when computers pass information one to another over some network, utilizes the idea that it's incredibly hard to factor a giant number like this. If you try to factor that number right there, you have to use a process in which the computer essentially goes through and systematically tries to make guesses as to where the factor might be. And so it'll try to find one of these 2 numbers. Once it's got one of the numbers, of course, it can just divide and get the other of those 2 numbers. But hunting down that first factor is an incredibly laborious process. A computer would find it eventually, if it worked long enough, But encryption technology relies on the fact that when it distributes a private key to one person and a public key to somebody else in a two-key asymmetric encryption system, the process of trying to extract one of those keys would take as long as factoring a number like this. And what you can see is that the equation that you have down here at the bottom emphasizes the amount of time it takes to factor a number like this depends exponentially on the size of this number right here. What does it mean to be exponential? What does an exponential curve look like? It takes off toward infinity. Now, a lot of people use the word exponential to refer to anything that isn't linear, but exponential is actually a stronger concept than that. It isn't just a polynomial like x squared or x cubed or x to the fourth. It's something that grows faster than any polynomial. Exponential curves take off exponentially. Here's a plot of what this looks like right here. This is the amount of time it would take to actually execute that algorithm, whether you're doing it with a classical computer, here's the classical result right here, or a quantum computer over here. What you can see is that for small values right here, when you have a small number you're trying to factor, the quantum computer is actually not very good. It takes much longer than a classical computer. A classical computer, for a number that has 100 bits in it, can solve that and factor that almost instantaneously, and the quantum computer won't work nearly as well. But because of the exponential time dependence of that scaling factor, this right here is taking off to infinity and creating what, for all intents and purposes, can be regarded as a brick wall that you cannot get through. This right here is zooming up so quickly that if you've got something that has 1,000 bits in it, trace this thing up to this location right here, how long does it take to factor 1,000 bits? Yeah, this is a logarithmic scale right here, which means that this thing right here is going to take 10 years to factor that. Now, if you had the world's most powerful computer and you had some advanced technology, this is projecting things 30 years forward, that might be a thing you get that number down a bit, but it won't help you all that much because look how steep this curve is right here. Even if you slide this curve over a little bit, it's still not going to make all that much difference. If you jump from 1,000 up to 2,000 over here, you'd be in a position where it still takes 10 years, even if you've got the best technology on Earth. Factoring 2,000-bit numbers is something that's going to be well beyond the capability of any person to implement on any computer for the foreseeable future. And so standard encryption techniques depend on the idea that you can rely on factoring algorithms taking much too long to extract the key that's required to break the encryption. Now, would you care about that? You know, this guy down here at the corner, right? He really wants to read your emails, especially if you work for the U.S. State Department. This is Vladimir Putin over here. And you know, the presidential election this year has demonstrated the virtues of having good encryption technology. If you don't have good encryption technology, some hacker is going to get to your server and read your emails. Maybe it contains something embarrassing that will cause you to lose your presidential election. That would be horrifying, right? And so, when you go over to this table right here, you can see all of these standard crypto system techniques right here. This is supposed to be a list of several different crypto systems. I'm not sure why that came out looking like it did. It's not just RSA. RSA uses a factorization technique right here. But there are lots of different techniques right here that work the same way, and quantum computing will reduce that time dependence to that flatter curve, that polynomial curve, and break all of those systems. There are some other ways of providing security, however. So maybe you might just say, well, if that happens, if that day ever comes when quantum computers are everywhere, we'll just switch to a different encryption technique and that problem will be solved. But at least in the interim, there'll be a situation where all of a sudden your technology is outdated and everything is insecure. So that's one reason why this might be a big deal. And another possible application is quantum simulations. If you do a simulation of a quantum mechanical system, at the moment you have to do that on a classical computer, right? Because we don't have any quantum computers to run this stuff on. What types of techniques do quantum computational chemists use in order to figure out the structure of some molecule? Where's De Boer? Is he in here? He's got to be back there somewhere. Now, what's an example of a program you might use to calculate the ground state configuration of some molecule?
Games?
Yeah, games, or Gaussian, or something like that. Yeah. And I've run lots of simulations on programs like that back in my undergraduate days. They existed even back then. Those programs are useful for fairly small molecules. Suppose some biologist came to you and said, I've got this really interesting protein. It's kind of a small protein. It only has about 400 atoms in it. Can you just load that thing onto Gaussian or games and run it for me? But what would happen if you tried to do that?
Well, you could do it at a lower level of calculation. Like a
yeah, you probably have to
mechanical.
simplify your basis set quite a bit. Well, what's the problem that's going on? Why would you not want to try to run, say, an entire DNA molecule on Gaussian?
Well,
It's terrible scaling behavior.
You'd probably be gone from eternal long before.
Yeah, I mean, in principle that can run, but the amount of memory you'd need would be absolutely astronomical. The size of the basis set would be absolutely enormous, and the kind of time it would take to run it would be longer than the lifetime of a human being. And as a consequence of that, it turns out that classical computers are just not very well equipped, even when they can do things in polynomial time, to tackle large quantum mechanical systems. And quantum computers, even the very simple, primitive, proto-quantum computing methods that we have today, are better at solving certain types of problems. If you want to model something that's intrinsically quantum mechanical, the right way to model that is by using a quantum computer. As it turns out, classical computers are great at representing classical systems in which things have definite, well-defined variables, and quantum computers are good at representing quantum mechanical objects that have this probabilistic-like behavior that we described earlier. Okay, this is from an article in Nature. You can look up the article in Nature. It's by Jeff Broomfield if you want to see more examples of possible applications that have already been developed even before the onset of powerful quantum devices. Okay, what's our big problem though? Why don't we see quantum computers everywhere these days? I mean, people have been trying to build these things for a while, but there's one big drawback that a quantum computer has. It can do everything a classical computer can do. There are a handful of problems for which it works vastly better, but it has this thing called decoherence. What happens is you take your quantum computer and prepare all of its registers in given states. Those registers will randomly decide to switch to different values. This is a bad behavior, right? If you have a classical computer, and your classical computer all of a sudden decides, I don't want a 0 to be there, I want a 1 to be there instead, what happens to whatever you just store them? Your information is lost, right? All of a sudden, your number is a different number. All of a sudden, your graphics file has a great big glitch right in the center of it because some pixel's been ruined. And if that keeps happening over and over again, your computer is going to be completely stripped of the information you tried to store in it. I've got some really bad news. That process, which happens at a glacially slow pace for classical computers are highly stable, happens incredibly rapidly for quantum computers. What's the number down here at the bottom? This is a number in nanos. How big is a nanosecond? 10 to the minus 9 seconds. It's a fraction of a microsecond. What this is saying is the decay function that represents the loss of information is going to be characterized by a nanosecond time scale. What that means is all the calculations that you want to do by using the qubits that you carefully prepared in your registers have to be calculations that complete in 10 nanoseconds or less. That seems like a pretty inconvenient computer, right? A computer that is going to suddenly stop having its information in it within 10 nanoseconds. I'm not going to go buy one of those. And the problem is that this behavior right here is ubiquitous behavior, and it gets even worse if you look at entanglement processes. The more you entangle bits to other bits, which is the source of all the power of quantum computing in the sense of being able to be parallelizable, comes at the cost of rapidly worsening this decay time record. We find the time for decay of the qubit entanglement can be significantly shorter than the time for local dephasing of the individual qubits. So life gets worse and worse the bigger we try to make our quantum computer. Today, the biggest quantum computer anybody has tried to build, if you believe the people at Google, the biggest quantum computer is probably on the order of 1,000 to 2,000 bits. Not megabytes, but bits. And even that's pretty controversial right now. If you want a really believable quantum computing implementation, IBM, I think just last month, came out with a cloud-based quantum computer that has 5 bits. If you want to, you can apply to IBM for some quantum computer time on their cloud, and they will give you a 5-bit quantum computer that you can use to implement things like Shor's algorithm or Grover's search algorithm for your own purposes, a 5-bit computer. Okay, we need some way of solving that problem. It turns out the way to solve that problem is to take a completely different paradigmatic approach to how to implement information. How do we protect that information from being lost to the environment? Well, classically speaking, what you try to do is make sure that your 1 state and your 0 state are widely separated in energy, right? You know, think about the little diodes that you probably messed around in some circuits lab at some point in the past. You take a diode, you bias that thing in the right direction, it suddenly flips on right there, but you need a pretty big voltage spread. You need to have some amount of voltage that you apply across that thing before that thing turns on. That's the order of a few volts, right? You know, that will not turn on if you give it a small fraction of that. And the big energy gap between those 2 states is the thing that's protecting your information. That energy won't come in randomly from the environment. It's not going to come in thermally from a few atoms jostling up against it and giving it a little bit of extra energy. It can only come from a nice big separation that comes from a little battery that you slapped into that circuit board to turn on your LED light. Okay. So we need some completely new approach, and to motivate that new approach, let me go ahead and show you kind of an embarrassing bit of self-disclosure. Okay, so here's an XKCD comic, and this is one of these things that if you're a sufficiently smart and sufficiently neurotic person, you're susceptible to. These little OCD type behaviors right here, like you can't step on the cracks of the sidewalk. Anyway, I have something that I've been aware of since I was young, a little OCD type tic, which is the idea that I hate exiting a building from a different door than the door I used to enter that building. And just to see, just a couple days ago, I searched on Google to see if I could see anybody else who had the same behavior. And sure enough, in the OCD subform of Reddit, there's somebody else who has that same thing working somewhere back in their subconsciousness. The idea that you're constantly being followed by this invisible string, and if you go out of the building through a different door than you used to go into the building, your string got tangled inside the building. You don't like that. You don't like tangled strings, right? I've been aware of this since I was in high school, at least. It's like having to line up all the books on the library shelf so their spines are at exactly the same distance. And it's a thing that you can't ever quite turn off once it gets turned on. You're always kind of aware of it working in the back of your head. But there are some contexts in which it's a beneficial property to have. There are some places where you actually wish that you could have a string that trailed along behind you. And one of those situations is this down here at the bottom. It's a game of 3-card Monte, or in this case, the shell game. You know, you go to the street con artist, and he's going to bet you $1 that you'll be able to figure out where this ball's been hidden after he starts to switch this thing around. And so, you know, if he's pretty good at putting up to the pattern like this, then he can start talking and hopefully distract you enough to forget where this thing is located. And then you'll have trouble pointing to the original location of where that ball was. Where's the ball? Middle. Yeah, okay. But if I were really smart, what I would have done is palm this thing using sleight of hand in my pocket so that all 3 of them were empty, and then you'd have to pay me no matter what. Okay. How can I make this incredibly easy? These things right here have strings attached to them. And what I can do is I can take these strings right here and take these strings down to the table. And what this will do is it'll leave a record in every single time one of these cups has been moved. I'll take this one down to the table over here. I'll take this one down to the table over here. And I'll take that one down to the table over there. Now what this means is that every single time one of these things moves, you'll be able to record the motion of that cup by looking at the trail that's left by its strings. So, you know, where do I put that ball?
Put it under the blue one.
Put it under the blue one right here. You can imagine doing some operation like this. I could swing this around like this, and then I could swing this around a second time. And you can see that once I swung that around a couple of times, the strings that have been left behind are recording the paths that this has taken right here. Now, if you're in a true 3-dimensional system, you can always disentangle these things, right? Lift this thing up and bring it back over here. But there'll be some record that's left behind of these because there's still a crossing right here. As you lift these up, you can see they've been braided together like this. And so even as you look out to that 3rd dimension, that information hasn't been permanently lost. It's been recorded as a braid. And that braid is a record of something that happened in time. And the good news is, in quantum mechanics, there are specific types of excitations that have that memory, that have an invisible string that follows along behind them at all times. And those objects are called anyons. Have people heard of bosons and fermions? Bosons and fermions. Examples of bosons, things like photons, gravitons. Examples of fermions, things like protons or neutrons. The lovely thing about those particles is that if you take those particles and rotate them around each other, they always come back to themselves. If you take a proton and move it around an electron and bring it back to where it started from, it'll look exactly the same way as it did before. In physics, there are exotic particles that obey different types of what we refer to as spin statistics. And those particles, when you rotate them around each other, change. That seems really counterintuitive, right? If I took this cup right here and rotated it around the other cup, you wouldn't expect it to suddenly be a different type of cup. You wouldn't expect it to turn from red to blue, or something to flip upside down, or do anything like that, because it's the same cup. You just moved it around in space, right? But in quantum mechanics, there are particles where when you switch this around and move this first particle around the other one, it'll pick up what we refer to as a phase factor. And a phase factor in quantum mechanical terms is like flipping something upside down like this. In terms of what the wave function looks like, it takes that wave function and flips it upside down when you rotate it around in a circle like this. And a consequence of that is that every time you move something around in a circle, it creates a modification of its phase that behaves very much like one of the strings they had over here. And those strings right here that represent the phase geometrically record the information that describes the operation I performed when I moved this thing. This line right here is a line that moves forward in time. These are world lines associated with the location of these things spatially in this direction, and as they propagate through time in this direction. You can imagine doing the same thing for me if every time I walked somewhere, there was a glowing after image of me, and you could see the front of the room filling up with my glowing after images. There'd be like a giant tunnel of me, glowing copies of me, extending back behind me. And that's exactly the thing that's happening over here. These are glowing copies of a particle, and the particle is really doing this. It's going shoot, 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 back and forth in the plane. And this right here is the after image as this thing is moving forward in time that shows you where it was located at some previous point in time. And the amazing thing about this is that as this process is occurring, the phase associated with this quasi-particle's wave function is recording everywhere it's been. It's telling you exactly where it's been at some point in the past. Now, you can actually use these braids right here to create logic gates. The operation of changing that phase by rotating one thing around another thing is in some sense equivalent to the flipping of ones and zeros that we saw back when we were talking about logic gates 7 or 8 slides earlier. And this picture right here shows you some sets of trinary bits right here. They're being wrapped around each other. And as those bits are being wrapped around each other, what they're doing is the equivalent of quantum logic. Anytime you make a braid, you can always turn that braid into a knot. How do you turn a braid into a knot? Somebody knows something about crochet. Around, you move it around, you keep it from becoming unraveled at the end.
Oh, you have to tie it off.
You have to tie it off, right. When you make a long set of pieces of yarn or string or whatever, you braid them together. At the very end, if you don't want it to unravel, you have to take the 2 ends and tie those 2 ends together. Now, in quantum mechanical terms, you can tie 2 ends together by taking 2 particles that are particle pairs, like an electron and a positron, and making them undergo mutual annihilation with each other. So if you can bring 2 particles that undergo mutual annihilation, then their world lines will suddenly combine with each other and vanish. And that's equivalent to taking a braid and transforming a braid into a knot. And at that point, we suddenly jump off into what we refer to as knot theory. Every time you bring things together and tie them off at the end and at the beginning, you end up with one of these unique configurations. Now these things can look messy after you tie them off the first time, but then you can simplify them down quite a bit. So this messy looking knot right here is actually fully equivalent, after a bit of manipulation, to what we refer to as a trefoil knot over here. And this thing right here that looks even messier is equivalent to a figure 8 knot. And this thing right here that looks nightmarish, this is one of Mr. Thistlewaite's knots right here, is just an empty loop over here. Lots of complicated looking knots end up being much simpler than they look, and so one question you might have is, well, how many unique knots are there? When you simplify down strings that have been braided and tied together at the top, how many unique configurations do you get? And this is a systematic list right here, I think owing to the theorist Louis Kaufmann, who works at the University of Illinois. This right here is a systematic list of the first few knots in terms of their general complexity right here that are absolutely unique. He came up with a unique nomenclature for knots, a unique way of describing them. And once you have these things right here, you can actually place them in what a mathematician would refer to as a homologous state right here. You can say that each knot can be represented by some other mathematical entity, like a polynomial right here. This is a one-to-one mapping of knots to polynomials. There are lots of people who do this for a living in mathematics. They take knots, they're doing knot theory, and they show those knots are equivalent to polynomials. Usually what they're trying to do is utilize the polynomials to simplify complicated-looking knots to prove that complicated knots are equal to simpler knots, but that process works in both directions. If you have polynomials, and you can map those polynomials back over to knots, then you could do mathematics by doing crochet. You know, you can take some complicated polynomial that you ordinarily try to work out by using some rules of abstract algebra, for whatever algebra it happens to obey, and resolve that polynomial by just taking some yarn and fiddling around with a crochet hook or some knitting needles or whatever it is, and then tying the thing off at the end, and looking at the final knot that you've got. The final knot that you've got, if you have a true homology between the polynomials and the knots, will give you exactly the answer that you would have found by doing some sophisticated mathematics in a mathematics course. Okay, so how do we, oh my goodness, I'm running out of time already. How do we actually implement this thing to do some useful quantum computation? What we need to do is create some quasi-particle excitation. And the quasi-particle excitations are going to be the things that leave behind them as a glowing trace in space-time a world line that represents that string that's being knotted together and it would represent topology. So this right here is a giant donut, right? This is a giant donut. Refer to this thing as a torus in geometry. And this torus right here is a surface. And the surface is a surface that's periodic, right? You can go around in this direction right here. You can go around in this direction right here. And both of those two periodicities right here map back to themselves after one full 2 pi rotation, 2 pi radian rotation. This right here is a surface on which I could make some individual qubits live. I could take one of these guys right here. This represents a qubit right here. And I could flip this qubit to either of its two sides. Here's a, say this is a 0, and this right here is a 1. Go ahead and stick a 0 right here. Go ahead and stick a 0 right here. Go ahead and stick a 0 right here. What I'm doing is I'm initializing this state right here to a given configuration. Let's go ahead and make them all one configuration to begin with. And this right here is an example of what you do to set up your quantum computer at the beginning of the calculation. Now, showing it in this configuration right here on the surface of a donut is somewhat inconvenient, and so anytime I actually plot this thing out on a picture like this, what I'm going to do is take my torus right here and slice it. I'll make a slice that goes through in this direction, a slice that goes through in this direction, and I'll end up with this right here. This right here is a sliced surface that shows you where things are located on this surface. And then what I can do is I can imagine taking a laser or some other device that changes the states of qubits and go in there and start to flip these qubits. Now, individually, these qubits are not reliable, right? I can flip this guy over to a blue right here, go from a 0 to a 1, but as I flip this thing from a 0 to a 1, it might not want to stay that way, right? It might decide in 15 or 20 nanoseconds, I'm sick of being a 1, I'll go back to being a 0 again. And of course, all these other things over here might do that as well. So I'm not going to focus on the qubits themselves as the source of my quantum information for the registers I'm using in order to do my computations. Instead, I'm going to counterintuitively focus on the empty spaces in between those registers. Thank you very much. Instead, I'm going to focus on this empty position right here. Now, empty spaces don't seem like they're very interesting to begin with, but it turns out that certain empty spaces can be remarkably useful and interesting. Anybody hear about tornadoes? What's a tornado? It's a location that's surrounded by swirling air. But there's nothing in the center of a tornado, right? If you're in the center of a tornado, no big deal, right? There's nothing there. This right here is like the location of a vortex. This is like a tornado right here. And if you go right in the center, you can define this thing in one of two configurations depending on what's around it. In this case right here, I've got 4 yellows right here. So this thing right here is one type of quasi-particle excitation. This has 3 yellows and a blue, so this is a different type of quasi-particle excitation right here. Note that every single time you flip one of these things, it'll actually make 2 different excitations at the same time. So excitations always come in pairs like this. If you flip one over here, then by necessity, you made another excitation that also exists over here at the same time. And that's interesting because it means that when we're living in a torus like this, we can actually control the emergence of these defects. If these things start to flip voluntarily, every time we make one, we'll be able to make another one. And what we discover is that these local defects, you flip this right here and just flip one of these right here, you get 2 of those side by side. If it moves over, you get another one right here, you get 2 of these side by side. Always come in pairs, and those pairs can always be kind of finagled back together. They can be corralled back together, so they come back to the same location and cancel out and make 0 again. If you flip this right here, what happens is both of these 2 things go away, right? I just removed errors from my storage device right here by recognizing locally that those 2 things could cancel out with each other. How big does an error have to be before it can't be removed by that process? It turns out the error has to go all the way around your torus, either in this direction right here or in this direction right here. Unless you have an error that's that big, the error is an unstable error, and the error can be trivially identified and removed by some kind of external code corrector, we refer to as a decoder. And this process right here is a process that we can implement in a variety of different ways. Now, I don't have time to show you all the information about how it's implemented, and instead what I'm going to do is jump right to the conclusion right here. So let me go ahead and pull up the simulation that I was showing at the beginning of class. And I was going to have Aaron come up and talk about it, but I feel like at this point we've run so far over that maybe the right thing to do is just show it to you. Right here. Okay, so this is where we start, right? You can see that this right here is a configuration in which there are a huge number of errors. All the errors consist of pairs of excitations that have been created by some random spontaneous spin slip of one of these registers right here. And every single time one of these things is created, so is created with a neighbor next to it. And what we're going to do is impose some kind of an external correction process, and that correction process is going to locate pairs of excitations that correspond to those errors and suck them in toward each other. So if you look closely, you can actually see that happening toward the end. Toward the end right here, you'll notice that these things start to pair off with each other, and you can see them actually get pulled in toward one another as they cancel out with each other. Those 2 canceled out, those 2 canceled out, and then we've got 2 that are left at the very end. There are always going to be 2 that are left at the very end because there are some real bits of information hiding inside of this, right? The real bits of information, pieces of information you want to use to do these braining operations right here. They'll exist in one-to-one homology with the actual problem that you're trying to solve. But anytime additional excitations arise as a consequence of random decoherence processes, we can always spot them locally and cause them to cancel out with each other by using the propagation of these quasi-particle excitations on the surface of the torus.
Yep.
Okay.
And unless we break now to relocate to lunch, we will cancel out all our students. So let's thank Dr. Hamilton, and we'll see you all.